Welcome to today's Nursery and Garden Industry Queensland webinar on energy efficiency in nursery pumping, how to reduce your pumping energy use. This webinar is funded under the Queensland Department of Natural Resources, Mines and Energy Farm Water Futures project. My name is Lex McMullen. I'm the Farm Management Systems Officer and the Farm Water Futures Technical Contact for the Nursery and Garden Industry in Queensland. Our presenter today is David Hunt, and David's been involved in various projects with plant industries, with different plant industries, looking at retrofitting irrigation systems in nurseries, looking at sprinkler performance in nurseries again, irrigation scheduling in nurseries, energy use in protected cropping systems, waste management, and most recently he's been involved with the QFF Energy Savers Plus extension project as a case manager and technical advisor to the nursery industry. So that's a little bit of David's background. So now I'll hand over to David and we'll get into the webinar and look at his insights into energy use in nursery pumping. So over to you, David.
Okay, thanks Lex. I will just share my screen here so everyone can see what we're doing. All right, so we all know what the topic's going to be, so let's actually have a look at what the webinar content is going to be. It's today we're going to look at what energy efficiency is, what affects energy efficiency, and how to measure energy efficiency. I'm going to present some examples along the way and talk about some options in reducing energy costs or improving energy efficiency. Towards the end there will be time for questions. But as Lex said, if anybody actually has any questions they'd like to propose, you can send it to him via the chat function and he will bring it up at the appropriate time. Also, please note that this webinar is not intended to actually make everybody an irrigation or energy expert. It's basically to give you some background information on what's involved in determining energy efficiency and to just explain some of the concepts. So if you do end up talking to a irrigation specialist about it, you might have a better understanding of how to ask him questions. So let's get into it. Firstly, energy efficiency is more than just not using electricity. You can actually use more electricity and still be energy efficient. Basically the best use of electricity and fuel to generate the most production for the least amount of energy input is a simple definition. But that can be broken down into two different concepts. There's energy efficiency, which refers to how efficiently the pump uses electricity to pump water. And then there's irrigation efficiency, which refers to how efficiently the irrigation system moves water around the system and applies it to the crop. Both will influence the cost of pumping and energy use. To take that a little step further, we can say a pump can be highly energy efficient, but the irrigation system can have poor application efficiency, or the irrigation system can apply water efficiently, but have poor pump efficiency. The idea is to get the right balance between energy efficiency and irrigation efficiency, and to give you the most economical or cost-effective way to irrigate plants. Just having a look at some basic pumping cost breakdown. Depending on the size and type of nursery or farm, a pumping system can account for between 10 and 8% of all electricity costs. Although the principles of plant production are similar, each grower will have slightly different pumping needs and should really assess their pumping system to determine if their pump is appropriate for their particular current and future irrigation requirements. And also remember, what works for one nursery or farm may not be appropriate for another farm or production system. It is very specific to each individual farm or nursery. And if we consider the lifetime costs of a pump, which can be anywhere between 5 and 15 years, but for economical reasons, most calculations are done over a 10-year period. So when we look at the combined total cost of the pump over that 10-year period, only about 5% is actually the original purchase cost. 10% is for maintenance, but 85% is the actual running cost of the pump over the life. So the more efficient the pump is to start with, the lower the operating cost over the life of the pump. The lower the running costs usually compensate for the capital costs. So you can buy a better quality pump up front and it'll pay for itself quicker over time. So what affects pumping energy efficiency? There is a large variety of different principles behind what affects pumping efficiency. These can be major issues like wrong size pump or inappropriate pipe sizes, or something as simple as partially closed valves, or even a salty solenoid valve will affect pump efficiency. Other things that affect pumping efficiency are control mechanisms, whether a pressure sensor is used, how old that sensor is, has it been calibrated recently, or has the pump been serviced in the last 12 months? Also, irrigation scheduling and sprinkler type will influence the pump efficiency and pumping costs. If these aren't designed to work in unison, then your pumping costs will be increased. Whoops. Another thing that affects pumping efficiency, or the one thing that, sorry, I've just lost my train of thought. Energy efficiency and pumping efficiency must consider the whole system, as each component within the system will actually affect the overall efficiency of that system. In some cases, the efficiency of a small component may be insignificant, but the efficiency or inefficiency of that component and each component will or could cancel out the benefits of installing a highly efficient pump. So I'm going to now talk about how you measure pumping efficiency and just give you some background information. As I said, there are separate performance indicators used to determine the efficiency of different irrigation components, but to test the efficiency of a whole system, all these must be considered. And luckily enough, the irrigation industry has come up with a benchmark or a standard that accounts for all the components within an irrigation system. This benchmark is the kilowatt hours per megalitre per metre's head, which is a mouthful. This accounts for all of the efficiency losses throughout the system to identify one single value. Now, the industry has a standard that they hold up as the benchmark, which is 5 kilowatt hours per megalitre per metre head. I'm more likely to say benchmark from now on instead of repeating that. If your system is operating at or below that 5 kilowatt hours per megalitre per metre head, then it is considered to be operating at its optimum efficiency. However, there are some cases where irrigation systems will operate above the benchmark, even though the pump is operating at its optimum efficiency. This is due to other influencing factors. So in some small systems, a pump will operate above the 5 benchmark rating, but it's basically because it's inherent in the pump. We'll get into that a little bit more later on. An alternative measure to that benchmark is the kilowatt hours per megalitre. This is easier to calculate and can be used to work out the cost of pumping per megalitre, which in some cases is more relevant to everyday use, because you can work out how much it's costing you to irrigate your crop. This unfortunately does not have an industry standard, and it does vary between crops and different industries. But the benefit of it is that you can use it as a comparison tool. So if you're wanting to compare how your irrigation system is running to another nursery, then you can use the kilowatt hours per megalitre costing to work that out. Also too, that will help you to do some before and after calculations. If you're looking at upgrading your irrigation system or changing a pump, you can use the cost of pumping to determine if it's going to be a better deal for you in the long run. So when you actually measure the cost of energy pumping efficiency, pumping energy efficiency, there's three basic values that you need to know. One is energy used by the pump, the flow rate of the system, and the operating pressure or total dynamic head. These values should be obtained using power monitors, flow meters, and pressure gauges, and recorded during actual operation of the system. It'll give you a much more accurate result if it's done with the flow meters and the power monitors and while the system is actually running under normal conditions. Alternatively, you can identify these values from equipment specification sheets and pump nameplates and use that to calculate an efficiency. But again, it's only an estimate, but it's an easy way to determine the cost of pumping. So just to run through some of the measurement examples, let's look at step one, which is measuring pump energy use. Again, if you have got an electricity meter connected to the pump and you can read that off, then that's the simplest and most accurate way to do it. Make sure that if you're reading kilowatt hours, that you read it off in a time period or time block of around about 20 or 30 minutes, because the idea here is that we want to get to a comparison of 1 hour. So you measure how many kilowatt hours your pump is using, record that. If there is no separate meter, and you can, turn off all other appliances and only run the pump and read off the electricity use. Again, if there's no other options, you can simply record the rating on the nameplate, but you must remember that this method is the least accurate, especially if the pump is old or a VFD is used. Reason being, an old pump may actually be using more energy than what the nameplate states. And if a VFD is used, then it's likely that it's going to be using a lot less energy than the nameplate suggests.
So just while we're there, David, I've got an example from a few years ago. We had a pump assessment on a bore pump, and during the course of doing that, they didn't know what was down the bottom of the borehole, what size motor there was on it, what size pump, and I measured the energy from their electricity meter. When I went away and did some calculations, I worked out that there was no way that they could have a motor of that size down the bore. And as it turns out, about 2 weeks after I did the pump assessment, the motor on the bore pump blew up. So it was obviously on its way out, and it was using a lot more energy than it should have. So that's one of the dangers. Yes, if you have a bit more information about what the energy use of the particular pump is that you're measuring, it might give you some clues as to how that pump's performing and whether it might need some maintenance or replacement.
Okay, interesting. Thanks, Lex. So I'm just going to move on now to step two in the how to measure pump energy efficiency. Step two, of course, is flow rates. You need to measure your flow rate of the system, and it is usually in litres per hour. If you've got a flow meter installed, then great. Simply record how much water is passed through the flow meter on, again, a 20, 30 or 60-minute cycle. If you haven't got a flow meter installed, then there is always using the old bucket and stopwatch to calculate how much water is being pumped. Basically, you just remove an end cap, or if there's a tap attached to the system, you can actually just run that and measure how much water. That'll give you a litres per second or litres per minute, which you then can adapt or convert. Or if nothing else, you can actually calculate the total output of an area using the flow rates from sprinkler specification sheets. Simply identify what a sprinkler emits and then multiply that by the number of sprinklers for the area. and that'll give you a rough indication of what that flow rate is. Then you will need to convert that from litres per minute into megalitres per hour, but that calculation can be done using a formula. And this basically, actually, once we get those first two values, you can actually calculate your cost of pumping from here. If you've got your energy use and you know what your flow rate is, you can divide the energy use by the flow rate, and that will give you a kilowatt hours per minute, basically, if you record it in litres per minute. But what we want to do is get to kilowatt hours per megalitre. So in the example here, we've got a 1.5 kilowatt pump. Our flow rate is 5,000 litres an hour. So we divide 1.5 by 5,000, and then to bring it to megalitres per hour, we multiply that by 1 million, which gives us 300 kilowatt hours per megalitre. And then if you take the cost of 1 kilowatt hour from your power bills, in this case, we're using 25 cents per kilowatt hour. You'd multiply that by the cost, and we end up with $75 per megalitre, which is how much it costs to pump in this system. Now that can be used, as I said before, as a comparison that if you wanted to change your pump, you could do the same calculation with the different pump rating in there and work out what the new pump's going to cost you. In some cases, it may be better or worse, and we'll see that in a couple of slides' time. But to actually finish the energy efficiency calculations, we need to include the total dynamic head. Total dynamic head can be difficult to measure if you don't have the correct equipment, because it's very hard to account for friction losses and so forth in the system, and the height of the pump above water. There is a rough way, a rule of thumb, to calculate the total dynamic head using operating pressure. You read the pressure at the pump if you've got a pressure valve connected to your system. You take the pressure at the pump in kilopascals, and then you divide that by 10. And this is an approximate value, an approximation of the total dynamic head. And once you divide that by 10, you can add the difference in height from the pump to the water level. And the example we've got here is that a pump system or irrigation system is working on 540 kilopascals. We divide that by 10 to give us 54, and then we add the 2 meters difference between the pump and the water level, which gives us 56 meters of head. It is a rough estimate. Lex has actually pointed out to me that the true conversion factor is 9.8 rather than 10, but as it's a rule of thumb, you can use 10, but you have to keep in mind that this is an estimate only. Once you've got those values, we can now work out what our efficiency rating is and what it's really costing. So to follow that through, we've got a 1.5 kilowatt pump, we've got a flow rate of 5,000 litres per hour, and we've got a total dynamic head of 56 meters. Putting that into the formula and then dividing the 300 kilowatt hours per megalitre by the total dynamic head, we end up with an efficiency rating of 5.4 kilowatt hours per megalitre per metre head. Now, in this case, 5.4 is so close to 5 that you wouldn't even question that. That's an efficient system. And we can take that. But if we were to look at that same example with a 5 kilowatt hour pump, we end up with 17.9 kilowatt hours per megalitre per metre head, which is effectively 3 times the acceptable benchmark. So this is where we're going. You can actually do these calculations, and even though it's a rule of thumb, it'll give you a ballpark figure of how efficient the system is. Now, some people may actually say that the system works fine and that's just a number. What does it really mean? So if we actually now take that and look at the cost of pumping, as we worked out previously, the 1.5 kilowatt pump costs $75 per megalitre to pump. but the 5 kilowatt pump actually costs $250 per megalitre to pump. This is pumping efficiency. It all comes down to how much you pay for pumping, and I think everyone would say they prefer to pay $75 per megalitre instead of $250. If we assume that this is a nursery and that they only use 1 megalitre of water per month, and there's no adjustment for seasons, then that means that there is a $2,100 difference per year by using a 5 kilowatt pump instead of a 1.5 kilowatt pump. And yes, they may be completely different scenarios, and a 5 kilowatt pump may not be appropriate, but this is purely just for example's sake. I'm going to take this a step further, because although pumping systems are critical, pumps are critical to an irrigation system, another factor that affects irrigation efficiency is the pipe sizes. So let's have a look at what happens if the wrong pipe size is used. Okay, the scenario is, you want to replace your main line and extend that main line to expand your nursery. You need 200 meters of main line, and you have a look around and you decide that there's a 32 millimeter diameter pipe for $341, or there's a 50 millimeter pipe that you can buy for $728. Now, both of them will provide the flow rate that's needed. In this case, it's 7,200 litres per hour, but the 32 millimeter pipe is cheaper. And you think, well, that's a good deal. I'm saving myself $417. But when we put that into the cost of pumping scenario, we end up with a 32 millimeter pipe actually increases the cost of pumping to $105 per megalitre. And the 50 millimeter pipe is only $11.50 per megalitre. Tenfold difference. So in actual fact, there's a $93 per megalitre difference by using the different pipe sizes, and that $417 you save on buying a small pipe only lasts for the first 4.5 megalitres. After that, you're actually paying an extra $92 per megalitre pumped. So why is that? That's because the 32 millimeter pipe actually has higher friction, and it needs a bigger pump and more energy to push the same volume of water through that smaller pipe. While the 50 millimeter pipe has the lower friction, it can use a smaller pump, or it can use a large pump with a VFD controller, which will actually reduce the energy use. And so it actually saves you considerable amounts of money. This is why it's very important to design and install an irrigation system correctly to suit the actual business requirements. Now I'm going to take this one step further, and I'm going to put this into a real world example. This nursery actually is currently part of the Energy Savers project, and they're going through upgrades right now. So this kind of gives a good example. The problem was that the nursery owner bought the nursery in 2012, an old nursery, and he started to resurrect the nursery and intended to actually expand production. The existing infrastructure and irrigation system was used and was in reasonable condition, but he changed the sprinklers to suit the different type of crop that he was growing, and all seemed to work well. However, irrigation ran for 12 hours per day. He could only irrigate one zone at a time, just to meet the plant needs. Now, the first solution, or the initial idea, was simply to use that existing system and just extend it. Problem being is that it increased his time to irrigate the nursery to 18 to 20 hours per day. The pump was operating at a much higher level. His cost of irrigation went up to about $7,500, which was a 47% increase. And he could still only irrigate one zone at a time. So when we actually looked at another option of just putting in a bigger pump and using the same main line, the cost of pumping actually came out to $227. Sorry, I didn't mention previously that we worked out his current pumping was costing him $126 per megalitre, and his pump efficiency was at 7.9. So it's reasonable, but if he was to just simply put on a bigger pump, the cost of pumping went up to $227 per megalitre. So this is one of the benefits of using this particular method. When we decided to look at another option of actually redesigning it and replacing the pump and main line, it came out as a much better option. So instead, it was decided that the pump and main line would be replaced. The pump was a 4 kilowatt pump, and the main line went from a 50 millimetre to a 90 millimetre main line. Cost of pumping was reduced down to $57 per megalitre as opposed to the $126 or $227. His pumping efficiency rating came in at 5.4, and the overall cost of implementing the new pump and main line was $7,500. But over that, by doing that, he's actually saved himself a little over $1,100 per year in pumping costs, and that's basically paid for the upgrade in 6 years. But the real benefit of all of this was that he could actually reduce his irrigation down to a window of 6 to 7 hours. And then he could actually use the solar power generated by his on-site solar PV system to irrigate, to power the irrigation. So effectively, it didn't really cost him to irrigate because it was all solar generated on site. Also, by putting in the new pump and main line, it's actually reduced the repair and maintenance costs for that irrigation system over time. So it was actually the best option. It saved money. Yes, he had to redesign things. Yes, it cost him $7,500 to do, but it saved him money and energy costs in the long run. Now, this highlights the benefits of a well-designed and correctly installed irrigation system. And in reality, though, most nurseries will retrofit or extend an irrigation system as needed with what they have on hand, or install a bigger pump to compensate pardon me, for the increased irrigation requirements. But before you actually look at upgrading a pump, you need to ask a few questions as to why you need to upgrade. What is wrong with the existing system? Is the flow rate an issue, or is the pump the wrong size? Do you need to reduce time taken to irrigate? Is more water storage needed, or is the water quality an issue? Water quality will have an issue on pumping energy by blocking sprinklers and causing increased biofilm to grow in the pipes, reducing flow rates and increasing friction losses. A bigger pump may not be the solution, and a cheap deal now could actually cost you more later. So you need to talk to an irrigation specialist and then take the irrigation specialist design to your irrigation supplier, and don't just buy what's on the shelf or what's on special. Make sure you check with the irrigation specialist that any alternatives are appropriate substitutes for your system, because as I said, if you put in the wrong piece of equipment, or put in a wrong size pipe, you could actually be paying a higher cost for pumping than you need to. So I'm now just going to talk about some methods of reducing pumping costs and improving pumping efficiency. Now, this is broken down into a couple of categories. Management practices is one of them. And these can be just as effective as physically replacing equipment. So you've got to ensure equipment is serviced regularly as per manufacturer's recommendations. Poorly serviced equipment can actually use 10% more energy to overcome the heat and the friction within the bearings. Make sure that there is sufficient airflow around the pump, and any motors or even refrigeration condensers will benefit from this as well. Insufficient airflow will increase the heat within the motor, and the hotter the motor, the more energy is needed to do the same job. Also, if it's a dirty environment, dirt will get into the pump and get into the control mechanism, and it'll cause all sorts of problems and only increase your maintenance and repair costs. Pardon me. But the right equipment and the best quality, if you buy the right equipment and the best quality, you can afford quality. You can afford as this. No, sorry, I've just made a mistake there. If you can buy the best quality, or you can buy the best that you can afford, it will help to reduce your operating costs, and it also help to extend the life of the system. Now you need to assess the application rates. So you need to assess the application rate and the uniformity of application to ensure it meets the needs of your crop and there are no overly wet or dry areas. Not only can water use be reduced, but operating costs as well if the irrigation system applies water uniformly. Also, it is easier to schedule multiple irrigations if the irrigation system is uniformed and efficient. So also check and service control sensors, whether they be a pressure or a temperature sensor. Clean and calibrate them all. If you're using old pressure sensors or any old sensor, have a look at them, pull them out, have a look at them. Is the sensor rusted? Is there a buildup of debris on it? Just simply by cleaning that sensor, it will actually improve the efficiency of the system, because it'll send the right message to the control equipment. And sometimes these sensors can actually have an error factor of 5 to 10% just due to being dirty or not being calibrated. So certainly do that. To look at this from a design perspective, again, talk to your specialist. If you need to have any calculations done, they can do those for you. Use a correctly sized pump that matches the duty cycle required. We saw in a previous example how the right sized pump can actually save money. If you're using a bypass valve or a throttling valve, consider replacing the pump. It basically is saying that your flow rates aren't matching your requirements. If you do have varying flow rates, then have a look at installing a twin pump set or a multi-stage pump and a VFD drive or VFD controller to adjust the pump operation. If the pump requires a vastly different flow rate, so if you've got two very distinctly different systems or irrigation requirements, then perhaps you need to look at installing two separate pumps to operate at two different duty cycles. Again, ensure that the pipe size matches your flow rate and your operating pressure. Operating pressure, just a quick little aside, is probably one of the most important parameters that you can adjust when it comes to energy efficiency. If you change your operating pressure even by a few kPa, it can actually reduce your energy, your operating cost of operation considerably, or cost of pumping considerably. Make sure that you've got nice straight runs, fluent bends, no major crazy pipe work. The more bends you put in there, the more elevation there is, the more friction there is, the more energy is going to be needed, the higher the cost of pumping will be. Also, if you're actually using lay flat hoses, although they can be useful at times, they have a very high friction coefficient, and they will cause your pump to use more energy. So if you are permanently using a lay flat hose and you can replace it with a solid pipe, then do so. Again, ensure that your operating pressure matches your sprinkler specifications. Like I said, this can have a major influence on irrigation efficiency as well as pumping costs. A simple change to the operating pressure can actually reduce your pumping costs by half in some cases. And again, as I said, if you're using a throttling valve or a bypass valve, then certainly consider changing your pump to suit your requirements you will actually save a lot more money in the long run. And you should really take a whole system approach when you look at this stuff. Just looking at one component. So if your pump dies and you think, oh, I just need to replace the pump, and you go down and talk to your local guy and he says, oh yeah, I can replace it with this. Just check to make sure that it is appropriate, and look at the whole system. So does the pump provide the right flow rate and operating pressure for the sprinklers? The whole system approach should actually start with what the plant requires, how much water they require, and how you're going to apply it to the plant, and then work backwards to the pump. And that'll give you the most efficient system. So when you are looking at upgrading or changing any components in the system, you need to consider a few things. Are there any constraints on the system? Has energy costs improved or increased? Are there any water restrictions that you have to be aware of? Is the pumping station in the right place in relation to the water source and land elevation? There's no sense in having your pumping station at the top of a hill and your dam at the bottom of the hill and you're trying to pump water uphill before you then irrigate. That's just going to cost you more. Do you actually know what the optimum flow rate and operating pressure is for your system? If you don't, have a look, check it out, ask your specialist. Also, how is the system being controlled? What sort of monitoring mechanisms do you need in there so you can actually manage your system better? Sometimes putting in a more elaborate irrigation controller that gives you more feedback to what's going on can actually help you to tighten your scheduling, which will help to reduce the cost of pumping. So I wanted to actually just talk about variable frequency drives, VFD controllers. I know there's a lot of questions out there as to whether it's a variable frequency drive or variable speed drive. These can be very cost effective in reducing pumping costs, and they can be programmed for different operating parameters to suit different irrigation types and different scenarios on site. They can provide a range of benefits such as soft start, identify any pump problems. They can identify pipe blowouts and shut off the system, and in some cases, if there's an alarm connected to it, they can either send you an SMS or trigger an alarm to let you know that there's something gone wrong. They are more sensitive to changes in the irrigation system, and they will reduce operating costs. But by no means will they fix all problems in all situations. There are some issues that you have to be aware of, like the pump must be compatible for a start. If there's a large variation in operating pressures or land elevation, they can cause erratic pump operation, or if the pump is oversized and it needs to operate at low speeds for an extended period of time, that can lead to the pump motor overheating, because a VFD drive, the way they call it a variable frequency drive, because the mechanism adjusts the frequency of electricity going to the pump, just like a volume knob on your stereo. So it turns down the frequency, therefore the speed of the pump drops, or you can turn it up and therefore the speed of the pump increases. If you've got an old single speed centrifugal pump, a VFD may not be the best way to go, because some of those old pumps just weren't designed to be manipulated that way. Also, the situation needs to be assessed by a pump specialist to determine if the VFD drive can be installed on an existing pump. As I just said, if that pump is not appropriate, then you may have to replace your pump. VFD drives or VFD controllers can be expensive, so you don't want to fork out $5,000 put it onto a pump only to have your pump blow up a couple of weeks later. And besides, you can buy combined pump and VFD packages that are much more economical to purchase and install.
And just on that, topic, you need to really assess before you put the VFD in or put a pump with a VFD on whether you're going to get a reasonable payback. And that comes back at least partly to how much you're using the pump. If you've got a situation where, yes, you have big variations in your flow, and that indicates that the VFD would be a good thing to put in, but you're only using the pump for an hour a day, it may take you 25 years to get your money back on energy savings with putting that system in. So you've got to keep those sorts of things in mind. VFDs are one piece of equipment that, while they weren't designed for nurseries, they're very applicable to the way that most nurseries run, but they're not necessarily applicable to every situation.
So true. You can also buy something along the lines of a VFD for other motors. So in the case of greenhouse climate controls, where you have they're automated and you have motors that open and close vents, you can actually get small motor controllers that do a very similar sort of thing. They monitor the power going into that motor and they adjust the power according to the amount of torque or stress that's being put on that mechanism. And they also save you energy. But again, like Lex just said, you've got to make sure that the component that you're using, A, is compatible, and B, whether or not it's going to be economically viable. You know, there's no sense in buying a Rolls Royce if you're never going to get the money back for it. Pardon me. So again, if the system is designed properly, correctly installed, and managed correctly, it can actually have some unforeseen benefits. And I've got one more example before we move on to any questions or anything. In this example, we retrofitted a 15-year-old irrigation system that had been put together over years, and the nursery had tried to address some of the inefficiencies in the system, and the nursery owner knew that there were problems, but he actually thought it was more to do with water quality affecting how his system operated. He started to supplement irrigation with town water to try and improve the water quality, which kind of did, but also increased his water costs. He'd gone down and spoken to his local irrigation supplier and tried to improve the system by adding in extra sprinklers. He had several different types of sprinklers at varying heights. All these sprinklers required a different flow rate and a different operating pressure. He put in a larger pump to try and accommodate the changes in the system, but he still ran his irrigation system for 3 times longer than he needed to, just to irrigate all of his plants. And of course, by irrigating 3 times longer, this led to a large volume of nutrients being leached from the containers and caused constant wet areas around the nursery that then caused algal blooms, weed growth, and it increased the disease occurrence. He used a lot of chemicals to try and compensate for this as well. But when he joined the project, we had a irrigation specialist look at the system, and they redesigned the system and retrofitted the irrigation system. And not only was the overall water use reduced by about 40%, the town water use was reduced by 67%, which actually saved him $19,000. The pumping cost was reduced by about 40% due to water and energy efficiencies. The water quality improved because he wasn't irrigating so much, and they realised that they didn't need to use as many chemicals to control the pests and diseases as the wet areas dried up and the pest and disease problems tended to stop. It was a rather expensive retrofit. It cost about $77,500 to retrofit the whole system, but that also included a water disinfestation unit, and it also included an extra 200 metres of main line, which we put in there to give the disinfestation system the contact time required to do its job. It doesn't mean that we ran an extra 200 metres of main line around the nursery. Space was tight, so what we ended up doing was actually just connecting the two rolls, 200-metre rolls, together in their rolls, and then actually put them into the dam, which also helped to control the water temperature because his main line laid across the surface of the nursery. So in the end, that $77,500 actually returned an extra $24,000 a year in profit to him, basically because of the water energy savings. But not only that, it reduced his plant debts by 5%, which gave him an extra $6,500 worth of plants that he could sell on. We didn't record what the savings were in chemicals, but the owner did say to me that they'd actually were only using around about 20% of what they originally were in chemicals. He said he'd get his staff suited up and they'd put their PPE on and they'd get their spray packs and out they'd go, and they'd come back and they wouldn't have used the tank of chemical because they didn't need to. So instead of doing it every couple of days, they went to doing it maybe once a month. The result of that was that they were so impressed with the results that they actually purchased another old nursery and retrofitted it to best management practices. And now they've actually tripled the size of their business, and they have improved their work-life balance because they're not worrying about how they're going to pay bills, and they're not worrying whether their irrigation system is going to blow in the middle of the night. So a good or a well-designed irrigation system can provide other benefits apart from just saving money. And in fact, there's a couple of people I've spoken to who have done this, and one of the comments that they surprisingly say is that their work-life balance is much better and they sleep better at night because they know that they can trust the system now. So basically, in conclusion, energy cost savings can be achieved through a well-designed, correctly installed and well-managed irrigation system, but it can also result in other benefits. And as I've just said, it can reduce pump failures, it can reduce your water use and costs, reduce your plant debts, reduce nutrient loss through over irrigation, improve your water treatment or reduce your water treatment requirements. It will also prolong the life of the components in the system and reduce your maintenance and repair costs, but above all, it will increase your profits. So that's basically the presentation, but there are some resources and articles if people are interested in following this up on the NGIQ website and the Nursery Production FMS website. There's a variety of information there in the technical libraries. There's also some videos that have been done that talk through how to improve an irrigation system. And of course, if anybody has any further questions or would like to follow this up, they can contact either Lex or myself through the NGIQ offices. Pardon me. And that is effectively the presentation. If there are any questions, we can move on to questions. Thanks.
Okay, no questions there yet. So I'd probably just say, regarding pipe sizes, when you're installing a new system, certainly look at the relevance of your pipe sizes, because if something isn't right with the system, or you need to take into account that you're going to be putting in more growing areas, for instance, it's a lot easier to replace a pump than it is to replace the pipes. Mm-hmm. So better to if you're going to lean any particular direction, is to make sure that you've got an appropriate sized pipe for what you've planned may need to happen. And I think the big thing out of this, particularly in that last example that you gave, is that you need to look at the whole system, because we're talking about energy efficiency here, but these systems have much wider implications and improvements that can be made in other areas of the nursery, like pest control and water use and those sorts of things.
Definitely. There's a whole other swag of benefits that we could talk about from improving your irrigation system, and also there are a variety of different ways to reduce your pumping costs or to improve your irrigation and pumping efficiency. But it's not something that can be presented in a booklet or presented in a webinar. It's one of those things where somebody needs to actually assess the system and determine what is the problem. As Lex just said, it may not be your pump, it may be your pipe, it may be some other component in the system. So by all means, talk to somebody, a specialist, irrigation specialist or pumping specialist, to get your advice on this. I really haven't got anything else to add to that. Lex, have you?
Well, I thought maybe a bit more of an exploration of why VFDs work effectively to reduce energy use. It's not just the simple that the motor runs at a lower speed, and that means that if you halve the speed of the pump, that it halves the flow rate. But what that does is it reduces the energy use by a factor of 8. So this is a thing called the pump affinity laws, and what that means is that reducing the speed of your motor by a factor is going to have a huge impact on the energy use of that pump. So it's not a straight line relationship. Certainly think about using VFDs, but just keep in mind that they don't always, they're not always the most viable option for a particular situation.
They're not always a silver bullet. Yeah.
No.
Yeah. They are good, and they do a wonderful job, but in the right situation.
Yeah.
Okay.
Okay. So there's still no questions there, so we might finish this webinar. So thanks, David, and thanks everyone else for attending today's webinar. If you've got any further questions, you can contact either David or myself at NGIQ. As we've said at the start, we'll put this webinar up on the NGIQ website, and I'll send you out a link so you can look at the webinar later on. So we'll bring the webinar to a close, and once again, thanks everyone for registering and having a look at today's webinar. Thank you.
Thank you.